All right, thank you everyone for joining. This is Stuart Weiler, Director of CAD and PLM for Elite. I'll just give you a quick introduction about us, and then we'll start talking about Mathcad. So Elite is a PTC partner. We are also a manufacturing facility. You can see we have a couple different branches. So part of the Elite Aerospace Group is the Elite Engineering Services Division. And that's the division that I work in and my colleagues as well. But we also have a factory that produces metallic parts in the aviation sector. And I'd just like to mention this because we do use PTC products in our factory. So we use the various products from PTC to design, build, manage all the different engineering that we do. So we are a PTC partner, which means that we can sell and support PTC software. And today, obviously, the topic of discussion is Mathcad. So I'll be introducing Emily Pinto from PTC, the Virtual Center of Excellence, who will be giving us a look at the latest version, which is Prime 7. And before we do, just a couple quick things about that. Prime 7 is going to have a new engine behind it, which is going to be different from previous versions. And previous versions will not be sold going forward. So what you see today is the newest version, and PTC is recommending that you update to it as soon as possible. Previous versions will still have support, but you won't be able to start new licenses of it. So if you have any questions about that, please feel free to reach out, and I'll be happy to explain about that. There are ways that you can stay on older versions for a longer period of time. Happy to get into that as well. But today's session is primarily about the functionality and the look and the feel of the newest version. We wanted to introduce you to it, and we'll be happy to talk about the licensing aspect with you if you have any of those questions. So without any further ado, I'd like to introduce Emily Pinto from the Virtual Center of Excellence at PTC.
Hi, Stuart. Thank you. Hi, everyone. I'm Emily. I'm going to walk us through Mathcad Prime 7.0 today. I have a short presentation and a demo to show. So let me share my screen. Okay. Can we see that all right?
Looks good.
Okay, thanks. So I work, like Stuart said, I work in a group for PTC called the Virtual Center of Excellence. So we specialize in introductory demonstrations and conversations with customers going through our different products. I specialize in CAD and everything Creo. So I'm happy to go through the capabilities here. And if there are any questions, I'll do my best to answer, follow up with whatever I have to look into, and we're happy to have a further follow-up conversation about any of our PTC products. If you're interested in Mathcad or Creo or anything like that, just reach out to Stuart, and we'll be able to set something up. So today we're going to talk about Mathcad Prime 7.0. We have first to address, what is Mathcad 7.0? What challenges does it address? What engineering challenges? Software is useful, but what's the value that you get from that, and how does it change what you're doing now? We'll also talk about the solution, go through the capabilities. I'll show a short demonstration of Mathcad Prime 7.0 and talk about how that might be useful for you. Again, if you have questions along the way, feel free to throw them in the chat. And then Stuart, I don't know if you want to stop me and ask them, that's fine. If you want to save them for the end, that's fine too.
Yeah, if they come up, if they're relevant, I will just let you know. Otherwise, we'll collect them for the end.
Okay, perfect. All right. So what are the challenges that Mathcad Prime 7.0? What does it address? Mathcad in general, really. And the number one here is inability to capture, share, and reuse design intent. When you're creating products, you're making different decisions, engineering decisions for your model, for your assemblies, and there's reasons why you're going to choose one thing over another, why your model looks the way that it does and your products work the way that they do. And this is all to meet design requirements typically, right? And different things that you're engineering against. And so you need to be able to capture that thought process so that you can reuse it, you can share it with others for design reviews, you can validate against those design requirements, and then reuse the design intent if there's product updates or something later that maybe someone on a different team or in the future who didn't work on it the first time around, they're going to have to start from scratch if you don't capture all of this the first time through. And that's just very time consuming. It can lead to errors. Not the most efficient way to do it, but something that we see pretty often out in the industry. And this is mainly because there's a lack of process and tool standardization. Maybe you have design requirements coming in from different emails. You have different calculations done on different pieces of paper. You've written a program in some software calculation tool that you're doing this math, and you're making decisions on the fly, changing them out, and crossing them out maybe in an Excel sheet to figure out what you're going to do for your model. This makes it really hard to aggregate all of that data, to flow through your process, and to reuse any of it, right? You might know how you arrived at your answer, but nobody else is going to be able to figure it out. And if there's rework that needs to be done, it's going to be hard to go back and find, okay, well, where did I go wrong? We also see lack of early design validation. This means that these things are too difficult to do, and so you take your best guess and you try to validate, right? So you go to analysis or prototype, and often things are wrong. You didn't meet your design requirements like you thought you were going to, and you have to go back and do a bunch of rework. This is very time consuming, it's very expensive, and it's because you maybe used a guess and check type of a method, or you just went off of a past product that you've used. And having a tool that allows you to do that early design validation with equations and different tables of values, that's a really more effective way to do it, to get it right the first time through. So all of these are addressed by Mathcad Prime 7. This is our solution. It's from PTC. It's a digital engineering notebook that allows you to perform your engineering calculations and manage your design intent at the same time. So this is a standalone application, but you can work with it with your CAD system. And it does a really good job of combining the ease and familiarity of an engineering notebook, where you're going to write as if you were writing on a whiteboard. It's all natural math notation and it makes sense. But it also has a powerful mathematic engine that not only does your calculations, but also makes sure that everything written in that engineering notebook is completely up to date. So you're not going to have errors where you changed the units somewhere earlier, but you forgot to change them in a later calculation, and now you're working with different numbers that shouldn't be together. And so this is how Mathcad Prime, right? It uses that engineering notebook to kind of assist your thought process, assist your design, and have it all correct and documented at the end. So some of these capabilities, you can see here, this is an example, this orange document here. This is an example of a Mathcad sheet. It might look like how you would write in a textbook, how you would write on a whiteboard, or if you were writing them down on a piece of paper to do your calculations, what the equations really look like. A lot of times, if you're not using an engineering notebook where it has natural math formulas or format, on the right, that image on the right, it's a lot of programming. This is a very difficult thing to review. It's hard to see where you went wrong. It's not very intuitive, and you need to know the programming language, and so does the person who might reuse this information. So that's really one of the benefits of Mathcad, is that it's all in natural math notation, and that makes it super easy to not only perform your calculations like that, but also to manage that design intent. You can see exactly what you intended for your results. So it really does combine that ease and familiarity. It's easy to put it in this notation. Functions and formulas are very easy to write down in Mathcad. And then the math is really done on it. So it's not separate. It takes that natural math notation and does the calculation right from that information. It understands those formulas. It understands variables and vectors and things like that. It's like I mentioned earlier, right, an easy to use whiteboard interface. So you're not going to have to take time to learn a programming language, and your documentation is done as you're typing. You don't have to rewrite something. The actual calculation that Mathcad uses is also what would be most easy to understand if you're looking back at this in the future. It's a comprehensive mathematics engine. It has live math, so if any variable or unit or anything is changed, any value, all of the formulas and results that use those values, those results will update automatically. So nothing is ever out of date. Anything that you change is propagated all the way through your sheet so that everything's always up to date for what's written on the page. It has live text, graphics, and brings other programs in a single readable form. So you can bring things in like Excel and PowerPoint to show these graphics. Has a text engine where you can format things, much like you see here, to make it easy to understand. Manages all your units automatically. You never have to worry about multiplying by 1,000 or dividing by 60. Everything is going to be managed for you. And like I said, it actually watches over you, makes sure that everything is congruent and makes sense, and gives you a flag if there's something that shouldn't go together. And it's self-documenting. You don't, other than maybe some formatting, some headings and colors, you don't have to rewrite anything. You don't have to write out all your calculations, get out all your results, and then go back and have to define your variables in a way that's easy to understand. It's all done at once. So it makes it super easy to understand. What you see is what you get. That means that there's no funky formats that are going to go on if you're trying to print this out as a PDF or print as a hard copy or send in an email. The format that you see in your Mathcad view is how it's going to look when you export it. So and things aren't going to get moved around, images aren't going to not show up. It's going to look exactly like this. It has a rich numeric function library, so you don't have to type all of your functions in. It has a lot of these functions for you, but it also understands that function notation. So as you type in your own custom functions, it'll understand how to calculate that and use the variables that you're assigning to solve. You have a lot of plotting capabilities. X, Y, polar, and contour plots are all available. 2D, right? 3D, the contour you can see is highly you're able to format, highly formatable maybe. And you also have access to other programs such as Excel, where you can format all sorts of plots and bring those in as well. So it doesn't limit you in terms of visualization, makes it easy to do. So what's new with Mathcad Prime 7.0? There's a lot that's new. The big one is a standalone converter. So you can actually install legacy Mathcad, and it's not needed. Legacy Mathcad installs are not needed in order to convert your legacy Mathcad documents. So this one is a big deal. Or if you have Mathcad documents that you're using already that have documented past processes, you can bring those into Mathcad 7 much easier than before. We have combo box input control. So this addresses high priority gap between the legacy Mathcad and the Mathcad Prime, right? So it actually allows you to convert for all types of legacy Mathcad web controls. You also have that left-hand slide for definition, which is much very useful and awaited. We also have Symbolic Engine enhancements and updates. So a new Symbolic Engine that is built out further and has more recognition for different symbols that you might use. General usability improvements as well: scroll, focus, zoom enhancements, things like grid line control, and the ability to save as a PDF format. We also have an improvement to APIs. So we have a guide now in the help documents that you can go and read about all of the API capabilities that you have. Okay. So we'll move on now to the demonstration. Okay, so this is our intro to Mathcad 7 demo. And we can see that this is our shaft bearing analysis sheet, just an example, right, of an engineering calculation that you might want to do while you're trying to decide the dimensions of your different components. So up at the top, right, for a similar format, you have your tabs for all of the different ribbons that you might want to use. You have your text options that you can format this. You can have those grid lines in the back so it looks like an engineering graph paper. You can combine right, in order to document, combine your variables with text as a good explanation, and then include units. So here's the Young modulus is defined up at the top, and you can include your units there so that those will be the ones used when you use that in calculations below. A good idea here, define your variables. So these are highlighted as a color. They also are defined with units. You have your shaft length equation where you're adding those variables. And if you have any questions about what variables they are, that CAD part image has been included as well as a little diagram. Very easy to embed these into Mathcad. You can even bring them in from a live document so that if there's updates made to it, those would update as well. And that really allows you to define the variables completely so that you can do your calculations and know exactly what you're working with. So for this, we're going to calculate. We need to make sure that our shaft speed is going to be above the critical speed that we need for the shaft, which is one of our design requirements. And so we have a couple of equations here that we're going to use: the stiffness calculation, the critical speed, which is in green. That's the one that we're really solving for. But you can see those red boxes, right? They kind of work backwards from the bottom up. You need your CQ, and then in your CQ equation, you need your I, which is your second moment of inertia. And that's going to be included here. So you'll notice that it's very easy to type in this formula notation, this natural math notation. You can add in your multiplication, your parentheses, your fractions. This is going to be that outer diameter, capital D to the fourth, minus your inner diameter. And then as soon as you hit equals, it's going to give you the result. And it's actually using, right, the definition of pi, which Mathcad knows, as well as that inner and outer diameter that are defined above. Now the units are another benefit of Mathcad. Right now, SI is the defined system. So meters, the results are going to be given in meters, which is the default for SI. But you have a whole list of units that you can choose from. And you can either choose them from this drop-down menu. So for example, if you want to change to centimeters, and as soon as you hit enter, that will update your results. So like I mentioned, this is live math. So as soon as something is changed, all of the results and calculations will update to reflect the accurate and correct result based on what's written in the document. You can also change your units by just rewriting them. So millimeters are recognized by Mathcad. So as soon as you hit enter, it recalculates that as well. Down here are critical speed. Perhaps we want it in RPM. That number will update. And then we can also start experimenting. So as soon as one of your definitions are changed, it uses D in that formula for I, which gives you the CQ value, which gives you the shaft speed. So if you change D, it's going to update your critical speed of the shaft. And now you can see that would be pretty repetitive to have to go back and look at each option you have for the diameter to see what the speeds are. And so that's not very realistic, right, for an engineer to do that. So we've documented now how we got that critical speed of the shaft. But what if we want to run through a lot of different options for the diameters? That's actually what is set up right here. So the problem statement up at the top, can we vary the number of inputs per variable? And with Mathcad, yes, you can. So one thing that's useful to do is to set that threshold limit for the RPM. And then we're actually going to run on the left here, we see all of these equations. These are the same equations from above, but we're going to have those now in the for loop that you see so that it'll run through multiple values for each of those variables that we want to define, which is going to be capital D and lowercase d. Now, to assign multiple values to each of those diameters, we can use a table. So up here in the matrices and tables ribbon, we see the insert table function, and we have options for how many rows and columns we want. This inserts a table, and it gives us that header where we can define the variable, choose our units. These are going to be in millimeters, and then we simply enter in those values. So D would be 12, 7, 11, 8. And this actually defines them as vectors. So this isn't just a list, the way that we have this in here. It's actually going to define capital D and lowercase d as vectors. So if we highlight this, and then we can see that these are defined as vectors with millimeters as the units, because if you type in one of these variables, such as capital D equals, and you hit enter, it's going to give you that vector format. So if you change that to millimeters, it'll change that as well, back to that original definition. And so this is what Mathcad now recognizes as capital D. So you can see here that this whole concept of documenting while doing your calculations and doing it in an organized way, that means you're meeting all of your design requirements and taking everything into consideration. I hope that this example is really fleshing this out. We're not doing two separate tasks of documenting and doing calculations. If we do extra documenting, such as highlighting these tables and creating these variables in this way, it's going to help our calculations be faster and clearer. So it's no wasted time. It's not double the effort, right? It's actually going to help our calculations, and we don't have to go back and do it at the end. It's all going to be done for us. So in order to use these for loops, this is part of the programming in the math. So operators and symbols, you can see we have the programming option. And for loops are really useful. Actually, all of these programming options are really useful. You can put in conditional statements. You can put in if and else statements, if else, while loops. And this is where you would get your for loop. And basically what this does is you have one for loop for capital D and one for lowercase d. So it's going to run through every single combination of these two inputs that you could possibly have. And at the end, if you look at the bottom of that block, you can see that NC, which is going to be your critical shaft speed, and a design check. So what that does is it actually checks your result for each of these combinations against that critical speed that we had up at the top. And so the results then would give you, we have two different tables of results. We have the critical speed, which it's just a matrix C, and then we have the pass-fail matrix. So it would actually say for each of those results we get, whether or not that combination of diameters would pass our requirement or fail our requirement. Now, it's a little bit hard to understand those matrices because there's no labels, there's no headings. And so down here, we actually have a section where this little formatting line will give headings and labels to each of the rows and columns. Now, this whole area, if you see this dotted line, this is what we call an area in Mathcad, and the little minus sign over here, you have a plus or a minus sign, allows you to collapse or expand this area. So we don't necessarily need all of this formatting to be shown because all we want to see is the final formatted table maybe. And so all of this could be collapsed. It helps you clean up your document, doesn't distract from what's necessary. And then you can take it one step further and actually protect the area. So maybe you're not just cleaning up your document, but you're protecting company IP. You don't want people to see something that you're doing because it's sensitive information. So you can actually give this area a password and choose, do you want it to be expanded or collapsed? So collapsing it would mean you're going to protect that area. Only people with the password would be able to see this information. Leaving it expanded is an option to protect it. Maybe you wanted to make sure that nobody changes those formulas. So here you can see that you cannot expand it without the password. So if you go to expand that area, it'll ask you to give the password. So leaving it expanded is useful if you want people to see those formulas, be able to use formulas that are in here. But if you don't want them to be able to change or edit what's in this area, you can password protect it, leave it expanded, and then they won't be able to edit. They'll only be able to view. So these are the final tables here. These are the results. You can format those easily. You just select the area and you can highlight those or color them. Now with Mathcad tables, this is, this is a very formatted for Mathcad. You have the headings and the labels, and they're highlighted, but you can't highlight specifically the heading column or the label column. You can't do conditional formatting if the pass and fail need to be highlighted. But you'll see here we do have a table that is just that. The labels and headings are highlighted, and we have conditional formatting for which results passed and which results failed. And then you can see easily what diameters those are. So the way that you would get this table, it's actually an Excel component. And the nice thing about Excel components is that you can take advantage of the full capabilities of Excel and have them visible, completely embedded in your Mathcad worksheet. You can see it's a very seamless embedding. It looks just like an image or something, but it's actually live. It's live data. So these would update as if it was done right here in Mathcad. So in your input-output ribbon, you have the option for read Excel. This would read information in from Excel. If you already have data in an Excel sheet that you're using, you can read that in, no problem, read it into Mathcad, use it in calculations. You also have the option for Excel component, and Excel component goes both ways. So we're actually going to take the results that we have and the calculations that we're doing in Mathcad, push them into Excel, do some formatting, additional calculations, whatever it's going to be. Usually it's formatting plots and tables. And this is how we would get that into Excel. We're going to read in the shaft speed in RPMs, and we're going to read that into Excel starting at B3. We also are going to read in, starting at G3, we're going to read in that pass-fail data. So that's how Excel is going to get that information. It's right from the calculation results. So if those results update, so will the Excel sheet. You can see here we have that formatting done. And then if we have any changes that are made in Excel, such as coloring changes, conditional formatting changes, plot changes, whatever it might be that you're used to doing in Excel that has additional functionality beyond Mathcad, that will all be immediately reflected into your Mathcad document. These are live, so just like the math is live, so is this connection. The same is true for other components if you're using something from images from PowerPoint or something like that. You can see here that those color changes are reflected immediately. Now, to look at one more thing here, this section here repeats the above exercises using functions. So this is something that maybe you wouldn't do if you were actually doing these calculations for a project. You probably wouldn't do it two different ways in the same Mathcad document, but for this demo example, we wanted to show off this other way of doing it. And so you can have the same setup here where you have your variables, you have your moment of area, second moment of inertia, right? Your critical speed of shaft, have all of your different diagrams and images, and then we could define them, instead of defining them as those equations, we could define them as functions. And so Mathcad actually understands function terminology. So if you type in f of x, it will understand that is the start of a definition of some formula that you want to use with x as the variable. So it's going to be an expression that's a function of x. So you can define this expression as x squared, which is a function of x. So now if you type in f of 9, as soon as you hit equals, it's going to give you the result of that function with 9 as the input. You can also do this as a vector, so you're not limited. You can have your input to this function. So if it's going to be x, you could have it as a 3-variable vector. So here we could have 2, 5, 7, and then as soon as you hit enter, it's going to give you the results back, and that's going to be in that vector format because that's the input. So these can obviously get more complicated than x squared. You can have all of the same equations and functions that we did up there earlier defined in this way. One of the advantages of defining your functions in this way is that it makes it very easy to plot. So here, for example, we have a plot of that function. We can see that that shaft speed is in green, and that is for a variable of x is the outer diameter. That's along the x-axis. So we're going to vary from 9 to 20. And then the 9 millimeters is the set diameter for the inner the inner diameter. And so this red line here, that's going to actually be the critical shaft speed that we need to meet. And so for this, it makes it very easy to compare to our design requirements, because we can look at this, and we have tools such as this horizontal marker makes it pretty easy. You can see right at this intersection, okay, well, if our inner diameter is 9 and we need this minimum critical speed, an outer diameter to get that is going to have to be above 11.9 or above 12. And so that makes it very easy to understand what our design requirements are and how we're meeting those with the different components. So we could do a plot of all of these against each other. If we want to compare all of the different combinations that we have, we could do our inner diameter as 5 millimeters. That was another one of the options. Plot that in RPM. And then if we see the outer diameter, we can look at that intersection point of where it meets our design requirement, and that looks like it's going to be down a little bit further. Now we can change the appearance of this. We can format these plots pretty easily. It's up here in our plots tab. We can change the color, the thickness, change the symbol, our line symbol, dotted. And then this horizontal marker would show you that the intersection point down here is going to be at about 10.8 or so. And so we'd have to be above that. Now, of course, we can get more complicated with these plots. We can get more complicated with our functions, but we're understanding our design requirements. We're validating against our constraints the whole time. We're doing it in a very organized, orderly way so that we know our calculations are correct because we can review our work. It's also easy to present in a design review. Anybody else would be able to review our work and make sure that our logic is sound, that this makes sense. And then when we do decide to use a certain dimension or diameter in Creo or in your CAD system, you would be able to see, oh yes, our final result here that we chose is very clearly 9 millimeters by 14, 14 millimeters for the outer diameter, and then you can make sure that that is what's entered into your CAD model, so that you know you're actually designing the correct part. So when we have customers who use Mathcad in this way, what is the impact on their design process, right? What do they come back and tell us? So we can see that it's really easy to optimize these critical design and engineering processes when you're using a method such as this. We also see an improved product quality because you're doing your design validation early on, and you're able to review to find mistakes. So you're really making the most optimized product, or rather a product that you know is going to make it through their validation cycle the first time. You know it's going to work, and you know that this is probably a good use of your model. We see reduced time to market, fewer errors, fewer reworks, fewer times through that design process is going to mean that you're getting your projects done faster. You're getting them done correctly the first time, as well as product updates. It's not going to have to redo all of the work that someone else did a year ago. You're going to be able to take advantage of all of that and simply make some additions and updates. All of this really works to reduce development costs. You avoid errors, you avoid rework, whether that's rework on a project or rework for having to redo all of these calculations the next time through. And so you can really review the work of colleagues with a common format that everybody's able to understand and doesn't take up extra time just to document. And so this is really where a lot of that value comes in for our customers. And hopefully you see that this is value that you can achieve as well. All right, Stuart, that was all I had to show today, so I can pass it back on over to you.
Thank you. And we have not yet had any questions, so no need to interrupt. But if anyone does have any questions about Mathcad, now would certainly be the time to ask them. And of course, you are welcome to contact us after the fact as well if anything comes up later on.
Hey, Stuart, I'm sorry, this is Ricky Cribbs. I've been trying to send a chat message, but I'm not able to.
Oh, all right. Well, I'm sorry. Well, go ahead and ask away then.
Okay. Most of what, Emily, thank you. for the presentation. Most of what you showed seemed to be more or less existing Mathcad functionality. Can you summarize in more detail the differences between 6 and 7?
Yeah, I do have some documentation on that I can go over with you, or I can rather send over. But a lot of the big key elements, right, is that standalone converter where you're going to be able to convert legacy data. We also have that combo box input control, so you're able to do this type of a drop down. So you have multiple inputs for any given variable. Those are two of the big ones. The Symbolic Engine enhancements, we have improved symbols, the capability to recognize different symbols. So I know that this is relatively vague, as well as the usability with scroll, focus, and zoom enhancements. But, does this answer your question, or would you like me to send over some specific documentation?
If you could send something, that'd be great.
Yeah.
I just didn't know if it was more than this. So obviously you've already covered it. So that answers my question. Thank you.
Okay. Yep.
And actually, just to add quickly to what Emily was saying, some of it also is Mathcad, not Prime, but just Mathcad previous versions. I think the last one was 15. Some of the functionality from Mathcad compared to Mathcad Prime wasn't captured. And Mathcad Prime 7 is one of the goals was to sort of just close that gap so that anyone that was still using the legacy versions of Mathcad would have that functionality in Prime. So some of that is mentioned here, but I think in the material that Emily is referring to, it shows specifically what and some of those are. So some of that was in here, but you'll see that. And the idea was, of course, that way anyone that has that legacy version should have all of that same functionality going forward in Prime.
Thanks, Stuart, for clarifying.
I'm sorry, can I ask one additional quick question?
Please do.
When's this going to be out?
Great question. The release date for 7, I think, is Tuesday, but let me double check.
Oh, okay. That quickly. Thank you.
Yeah, it's very, very soon. I think it is mid to late March. Let me get you that exact date. I'll follow up in an email with you when I have it for sure, but I know it's right around the corner. Looking to see if I can find it for you right now, actually, but it might take me a moment. If there are any other questions, I'll keep looking while we take those. No, actually, Prime 7 is available today. I think it may have been made available as of today, just like records and books.